Imagine for a moment that you are standing outside on the clearest night you have ever experienced. No city lights, no clouds, no moon to wash out the sky. Just you and the full, overwhelming canopy of the Milky Way stretching from one horizon to the other like a river of ancient fire. Every point of light up there is a sun. Many of those suns have worlds orbiting them, planets held in gravitational embrace, warmed by stellar radiation, sheltered by the invisible leash of gravity that keeps them in their cosmic family. Now imagine a planet out there, a world perhaps as large as Jupiter, perhaps as small as Earth, that has none of that. No sun, no warmth, no light. It travels through the absolute darkness of interstellar space, completely alone, moving through the galaxy not because something is pulling it forward, but because something once pushed it away. It wanders. It has been wandering, perhaps, for billions of years. And it will continue wandering, in silence and darkness and cold, until the universe itself grows too old to remember it was ever there. These are the rogue planets, and they may be the most overlooked, most mysterious, and most strangely haunting objects in the entire galaxy. We talk a lot about stars. We romanticize them, name constellations after them, write poetry about them, build mythologies around them. We talk about black holes with a reverence bordering on religious awe, and we speak of neutron stars and pulsars with the excitement of scientific revelation. But rogue planets, these cold, dark, wandering worlds, have existed mostly in the shadows of scientific discussion, noticed only recently, understood barely at all, and yet potentially outnumbering every star in the Milky Way by factors that make your mind do uncomfortable things when you try to hold the concept steady. Some estimates suggest there could be hundreds of billions of rogue planets in our galaxy alone. Others suggest the number could be in the trillions. Trillions of worlds, traveling in the dark, completely alone. Before we go any further, ask yourself this. If a planet can survive without a star, what does that mean for life as we understand it? What does that mean for the assumptions we've been building our entire understanding of the cosmos upon? What if the galaxy is full of worlds we have never been able to see precisely because they carry no light of their own? These are not idle questions. These are questions that some of the world's most respected astrophysicists are asking right now, in observatories and universities and research institutions scattered across the planet, because the answers have the potential to fundamentally rewrite our understanding of where planets come from, where life might exist, and what the universe really looks like when you turn off the lights. Let's start at the very beginning, because to understand what a rogue planet is, you have to understand how planets form in the first place. And more specifically, you have to understand how the process of planetary formation is messy, violent, chaotic, and profoundly imperfect. When a star is born, it does not emerge quietly. Stars form inside vast clouds of gas and dust called nebulae, and the process begins when a region of that cloud becomes dense enough for gravity to overcome the outward pressure of the gas. Once the threshold is crossed, the cloud begins to collapse inward on itself, spinning faster and faster as it does. The same physics that makes a spinning ice skater speed up when they pull their arms in. The collapsing core heats up until nuclear fusion ignites, and a star is born. But most of the material in that original cloud doesn't fall into the star. Instead, it flattens into a rotating disk of gas and dust around the new star, what astronomers call a protoplanetary disk, or a circumstellar disk, and it is within this disk that planets begin to assemble. The process is called accretion, and it is both beautiful and brutal. Dust grains stick together. Pebbles form. Those pebbles collide and merge into larger rocks, called planetesimals, which collide and merge again, building up into protoplanets. This is not a gentle process. These collisions are violent. Worlds in early formation are struck again and again by other bodies, sometimes shattered, sometimes growing stronger from the impacts. The early solar system was an almost unimaginably violent place, and so is every early planetary system around every star that forms in this way. Now here is the critical point. Within these young planetary systems, there is an enormous amount of gravitational interaction happening simultaneously. You have the dominant gravity of the young star. You have the gravity of the various growing planetary bodies interacting with each other. And critically, you have the gravitational influence of gas giants. Massive planets that form relatively quickly in the outer regions of the disk and whose enormous gravitational pull can disrupt the orbits of every other object in the system. Think of Jupiter's role in our own solar system. Jupiter is so massive that its gravity has flung countless asteroids and comets to completely different orbits over the history of the solar system. Its influence has shaped the asteroid belt, redirected the paths of comets, and played a significant role in determining what the inner solar system looks like today. Now imagine that same kind of gravitational dynamics happening in a younger, more chaotic system, with planets that haven't yet settled into stable orbits. What happens when two gas giants form close together and their gravitational interaction becomes unstable? What happens when a young planet migrates too close to its star or too far out? What happens when the gravitational chaos of a young system reaches a critical point? Some planets get ejected. Not gently, not gradually, but violently expelled from their home systems by gravitational interactions so powerful that the planet's escape velocity is exceeded. Imagine a world. Perhaps a world with oceans, with a thick atmosphere, perhaps with the earliest stirrings of geological and chemical complexity, flung out of its solar system like a stone from a sling. In a geological instant, that world goes from being a member of a stellar family to being utterly alone in the interstellar void. The light of its home star, which once dominated its sky, fades over decades and centuries into just another point of light among billions, then dims and reddens and finally disappears below the threshold of visibility. Darkness descends, and it never lifts. This is one of the primary mechanisms by which rogue planets are created, and it is far more common than you might expect. Computer simulations of planetary system formation consistently produce large numbers of ejected planets. In fact, some of the most sophisticated models of early solar system dynamics suggest that our own solar system may have ejected several planetary bodies during its early history. You heard that correctly. Our solar system, the comfortable and seemingly stable arrangement of 8 planets that we call home, may have once had more planets, and may have hurled some of them into the interstellar void long before recorded human history. There is even a theory, which we will return to later in this story, that a hypothetical 5th giant planet in our early solar system was expelled by the gravitational influence of Jupiter and Saturn billions of years ago, and that this ghost of a world is out there somewhere in the darkness, still wandering. But gravitational ejection from stellar systems is not the only way rogue planets come into being. There is a second pathway, and in some ways it is even more philosophically striking. Some rogue planets may never have had a star at all. In regions of space where star formation is actively occurring, the collapsing process doesn't always produce a single star or even a binary star system. Sometimes the fragmentation of a collapsing cloud produces objects that are simply too small to ever ignite nuclear fusion. Objects that are planet-sized or brown dwarf-sized that form in isolation, directly from the cloud itself, the same way a star forms, but without ever achieving the mass necessary to become a star. These objects are sometimes called sub-brown dwarfs or planetary mass objects, and depending on who you ask, the question of whether to classify them as planets or as failed stars is one of the genuinely contested debates in modern astrophysics. The distinction matters more than it might seem. If a rogue planet formed in isolation, directly from a collapsing cloud of gas and dust, it has a fundamentally different history and potentially a fundamentally different composition and structure from a planet that was first part of a solar system and then ejected. Its atmosphere, its interior, its heat signature, all of these things might be different. And the question of whether it could harbor life, which we will absolutely be returning to in great detail, might also have a different answer depending on which origin story applies. This question of definition is not purely academic. It touches on something deep in how we think about what a planet is. The International Astronomical Union, the body responsible for official astronomical definitions, has defined a planet within our solar system as a body that orbits the Sun, has achieved hydrostatic equilibrium, meaning it is roughly spherical, and has cleared its orbital neighborhood. But a rogue planet orbits nothing. By the IAU's own definition, it arguably doesn't qualify as a planet at all. which is why some astronomers prefer the term planetary mass object, or planemo, when speaking about these wanderers. Others use the term free-floating planet. The terminology debate is ongoing, and it reflects a real scientific uncertainty about the nature of these objects that is not yet fully resolved. Now, here's where things start to get genuinely strange, and where the story of rogue planets transforms from being merely scientifically interesting to being one of the most startling and counterintuitive stories in all of modern astronomy. For most of human history, we could only find planets by detecting them in relation to their stars. The two main methods of exoplanet detection, the radial velocity method and the transit method, both rely fundamentally on the presence of a star. The radial velocity method works by detecting the tiny wobble a planet induces in the motion of its host star as they orbit their common center of mass. The transit method works by detecting the tiny dimming of a star's light when a planet crosses in front of it from our line of sight. Both methods are extraordinarily sensitive. Both methods have produced spectacular results. Thousands of confirmed exoplanets discovered, catalogs of alien worlds accumulating year by year. But both methods are completely blind to rogue planets. You can't detect a wobble caused by something that has no star. You can't detect a transit across a star's face if there is no star. So for a long time, rogue planets existed mostly as a theoretical prediction. The models said they should exist. The simulations of planetary system formation produced them in large numbers. But finding them observationally was a completely different challenge. A challenge that required an entirely different set of tools. The technique that changed everything is called gravitational microlensing. And it is, if you will forgive the enthusiasm, one of the most elegant and almost magical methods in all of observational astronomy. Gravitational microlensing is a consequence of general relativity, Einstein's theory of gravity, which describes gravity not as a force between masses but as a curvature of spacetime caused by those masses. One of the predictions of general relativity is that light, which travels through spacetime, follows the curvature caused by massive objects. This means that a massive object, a star, a planet, a black hole, can act like a lens, bending and focusing the light from a more distant background source in a way that temporarily brightens the apparent light we observe. When this happens with a star or planet passing in front of a background star, it causes a characteristic brightening event that astrophysicists can detect with careful photometric monitoring of stellar fields. The brilliant thing about microlensing is that it doesn't care whether the lensing object has a star. A rogue planet, dark and invisible, still has mass. It still curves spacetime. It still bends light. And as it drifts across the line of sight between us and a distant background star, it causes that telltale brightening event, a brief, symmetric spike of light that tells us something is there, even if we can't see the thing itself directly. The duration and shape of the microlensing event tells us something about the mass of the lensing object, and events caused by planet mass objects are characteristically short, lasting days or hours rather than the weeks or months typical of stellar mass lenses. The optical gravitational lensing experiment, known by its wonderfully apt acronym OGLE, has been one of the primary instruments of rogue planet discovery through this technique. Running since 1992 and based in Chile at the Las Campanas Observatory, OGLE has monitored hundreds of millions of stars in the direction of the galactic bulge, the dense, star-packed central region of the Milky Way, looking for the characteristic brightening events of microlensing. Over decades of observation, OGLE has detected numerous events that have the signatures of planet mass lensing objects with no apparent host star nearby. Each of these events is a ghostly fingerprint, a momentary flash of borrowed light that reveals the passing of a world in the dark. In 2011, a team of astronomers published results from the MOA Microlensing Survey, a collaboration between Japanese and New Zealand astronomers using the Mount John University Observatory in New Zealand, that caused a genuine sensation in the astronomical community. Their analysis of microlensing events detected by the survey found evidence for a population of free-floating planetary mass objects with masses roughly comparable to Jupiter, and their statistical analysis suggested that these objects were surprisingly common, potentially more common than stars in the Milky Way. The paper, published in the journal Nature, estimated that there could be roughly twice as many Jupiter-mass free-floating planets as there are stars in the galaxy. In a galaxy containing roughly 200 to 400 billion stars, that means the potential number of Jupiter-mass rogue planets alone could be in the hundreds of billions. Pause on that for a second. Let it sink in. Hundreds of billions of Jupiter-sized worlds, dark and cold and wandering, in our galaxy alone. And that's just the Jupiter-mass ones. Add in the smaller rogue planets, the Earth-mass ones, the Neptune-mass ones, the super-Earth-mass ones, and the numbers become genuinely staggering. Now ask yourself this. When we talk about finding life in the universe, when we point our telescopes at nearby star systems and look for Earth-like planets in habitable zones, are we looking in the right places? Are we even asking the right questions? Let's talk about what a rogue planet actually looks like. Or rather, what it would be like if you could somehow find yourself on the surface of one, since of course they are virtually invisible to any telescope because they emit no visible light. The first thing you would notice, assuming you somehow survived the transit to such a world, is the darkness. Not the darkness of a moonless night on Earth. Not even the darkness of the far side of the moon during a lunar eclipse. The darkness would be absolute in all directions except for the stars. And the stars, magnificent as they are, cast no meaningful light on a planet's surface. The only illumination would come from the faint, diffuse glow of starlight spread across the sky, and on most rogue planets, that would not be enough to see by. The surface would be as dark as the inside of a sealed vault. The second thing you would notice is the cold. And here, the story becomes more complicated and more interesting than you might expect. Intuition says a rogue planet must be incredibly cold. And on its surface, you would be right. Without a star to warm it, a rogue planet's surface would be exposed to the approximately 2.7 Kelvin background temperature of the cosmic microwave background, which is to say, just barely above absolute zero, about negative 270 degrees Celsius. The surface would be a frozen wasteland of extraordinary severity, far colder than anywhere on Earth, colder than the surface of Pluto, cold enough to freeze every atmospheric gas that condenses at anything above absolute zero. But, and this is the part that begins to make your assumptions about what a rogue planet could be crumble into fascinating possibilities. The surface is not the whole story. Not even close. Planets generate their own heat from the inside. This is called geothermal energy, or more precisely radiogenic heat, and it comes from the decay of radioactive elements deep within a planet's interior. Every rocky planet contains radioactive isotopes, uranium, thorium, potassium-40, that release heat as they decay. This process is entirely independent of any external star. The Earth's interior is significantly warmed by this radiogenic heat, and it has been releasing this heat since the planet formed, over 4.5 billion years ago. On Earth, the contribution of geothermal heat to surface temperatures is small. The sun is overwhelmingly dominant. But on a rogue planet with no sun, the internal heat is the only game in town. For a rocky planet with Earth-like composition, the geothermal heat alone might not be enough to maintain liquid water on the surface. The surface would still be brutally cold. But here is where another factor comes into play: a thick hydrogen atmosphere. Work published by theoretical astrophysicists, including a highly influential paper by David Stevenson of the California Institute of Technology published in 1999 in the journal Nature, explored the possibility that a rogue planet could maintain liquid water on its surface and potentially support life if it were endowed with a thick enough hydrogen-rich atmosphere. Hydrogen is the most abundant element in the universe, and a planet that formed from the gas of a protoplanetary disk, or that captured a thick primordial atmosphere, might retain a substantial envelope of molecular hydrogen. Because hydrogen is an excellent greenhouse gas at high pressures, much more effective than carbon dioxide or water vapor. A sufficiently thick hydrogen atmosphere could trap the geothermal heat radiating from the planet's interior, maintaining surface temperatures well above the freezing point of water even in the complete absence of a star. Think about what this means. A world in total darkness, with no sun, utterly alone in the interstellar void, could potentially have liquid oceans, could have temperatures warm enough for chemistry, could have conditions that, at least in principle, satisfy the most basic requirements we associate with habitability. Stevenson's 1999 paper was met with a mixture of excitement and skepticism. The idea was creative and theoretically sound, but it raised obvious questions. Would the hydrogen atmosphere survive over geological timescales? Would the geothermal heating be sufficient? What about the UV radiation and stellar wind that strips atmospheres from planets? On a rogue planet, the threat of atmospheric stripping by a host star's solar wind is absent, which is actually a point in the rogue planet's favor. The interstellar medium is not entirely empty, but it is orders of magnitude less hostile to a planet's atmosphere than the energetic output of a nearby star. Subsequent theoretical work has both refined and complicated the picture. Some models suggest that even smaller rocky planets, with masses comparable to Earth or a few times Earth, could maintain subsurface liquid water for billions of years using geothermal heating alone, even without a hydrogen atmosphere. This is because the ice itself, if thick enough, acts as an insulating layer, trapping the internal heat below. The model here is something similar to what we think happens on Europa, Jupiter's moon, where a global ocean of liquid water is maintained beneath a thick ice shell despite Jupiter being at roughly 5 astronomical units from the Sun and receiving very little solar energy. Europa's ocean is maintained not by solar heating but by tidal heating from Jupiter's gravity, a different mechanism, but the key point is that liquid water doesn't require direct sunlight. Life as we know it requires liquid water. Life as we know it does not necessarily require sunlight. There is life on Earth in environments that receive absolutely no sunlight. The deep-sea hydrothermal vent communities, discovered in 1977 when the research submarine Alvin descended to the Galapagos Rift and found thriving ecosystems clustered around volcanic vents on the ocean floor, shattered the assumption that all life on Earth ultimately depends on photosynthesis and solar energy. These communities of tube worms, crabs, clams, bacteria, and archaea survive entirely on chemical energy. Specifically, the energy available from the chemical reactions between the hot, mineral-rich water ejected by the vents and the cold seawater. This process is called chemosynthesis, and the organisms that perform it are some of the hardiest and most ancient forms of life we know of. They have no need for sunlight. They have no need for photosynthesis. They need only heat, water, and chemistry. If life can exist at the bottom of Earth's oceans in the total absence of sunlight, supported only by geothermal energy, then the conceptual leap to life existing in the subsurface oceans of a rogue planet is not as enormous as it first appears. It is still a leap. We have no confirmed evidence of extraterrestrial life anywhere, let alone on a rogue planet, but it is a leap that serious scientists are willing to consider seriously. And this is exactly why the question of rogue planets matters so much beyond the purely physical and astronomical. It forces us to revisit one of the deepest and most cherished assumptions in astrobiology, the concept of the habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the range of distances from a star within which a planet with sufficient atmospheric pressure could maintain liquid water on its surface. Too close to the star and the water evaporates into a runaway greenhouse effect. Hello, Venus. Too far from the star and the water freezes permanently. Hello, early Mars. But just right, the way Earth is, and you have liquid water, and with liquid water, the possibility of life as we know it. The habitable zone concept has been enormously productive. It has guided the search for exoplanets likely to harbor life. It has shaped the design of space telescopes and the priorities of observational programs. It has been the backbone of astrobiology for decades. But the habitable zone is a star-centric concept. It only makes sense in the context of a star. A rogue planet, by definition, is outside any star's habitable zone. It is beyond every habitable zone, in the cold void between the stars. And yet, if the theoretical models are right, it might still have liquid water. It might still have conditions compatible with life. The habitable zone concept is not wrong, but it may be incomplete. It may describe one pathway to habitability while leaving an entire category of potentially habitable worlds entirely uncounted. Sarah Seeger, a MacArthur Fellowship recipient and professor of physics at MIT, has written and spoken extensively about the possibility of life in environments beyond traditional habitable zones, including the interiors of rogue planets. She has argued that we need to dramatically expand our conception of where life might exist in the universe, that our definition of habitability has been too Earth-centric, too star-centric, and that the universe may have found ways to support life in environments we haven't yet seriously considered. Seeger's work is careful and rigorous, and she is not making reckless claims. She is pointing out that our models of habitability are models, not laws of nature, and that the universe is under no obligation to comply with our intuitions. Let's come back now to the physical nature of rogue planets, because there is more to say about what they are actually like, and some of it is genuinely surprising. One of the things that makes rogue planets so difficult to study is that they are essentially invisible. They emit no visible light. However, they are not completely dark. A planet that has recently been ejected from its solar system, or that is young enough that it still retains significant amounts of primordial heat from its formation, will glow faintly in infrared radiation. Heat radiation that is invisible to the human eye but detectable by infrared telescopes. Young rogue planets, those formed within the last few tens of millions of years, may glow quite brightly in the infrared relative to older, colder ones. This has made infrared astronomy a critical tool in the search for and study of rogue planets, and it has produced some of the most exciting discoveries in the field. One of the most striking recent examples came in 2023, when astronomers analyzing data from the James Webb Space Telescope, the most powerful space telescope ever built, which began science operations in mid-2022, reported the discovery of what appeared to be a large number of free-floating planetary mass objects in the Orion Nebula, one of the nearest star-forming regions to Earth, approximately 1,300 light-years away. The Orion Nebula is a stellar nursery, a place where new stars are actively forming in vast clouds of gas and dust, and it is one of the most studied regions of space precisely because of the extraordinary window it provides into the process of star and planet formation. What the Webb telescope found there was unexpected even to experienced astronomers. In a study led by Samuel Pearson and Mark McCaffrey and published in 2023, the Webb telescope's near-infrared cameras detected somewhere between 40 and 540 extremely faint, red objects in the Orion Nebula, the large range reflecting uncertainty about exactly how many of the objects detected qualified under specific mass criteria that appeared to be free-floating, with masses in the planetary range, somewhere between roughly 0.6 and 13 Jupiter masses. Many of these objects appeared to come in pairs, which was itself a deeply puzzling finding. These paired objects were quickly dubbed jumbos, Jupiter mass binary objects, by the research team, and the term spread rapidly through the astronomical community and into science journalism. The existence of jumbos raises profound questions about how planetary mass objects form. The two main competing explanations for their origin, direct gravitational collapse from a fragmenting cloud, or formation in a protoplanetary disk followed by ejection, both face challenges when applied to binary planetary mass objects. If they formed in a disk, how did two planet mass objects stay together after being ejected? The gravitational binding energy of a binary with two Jupiter mass objects separated by substantial distances is very small, and the violent dynamics of ejection would be expected to easily break such a pair apart. If they formed directly from a collapsing cloud, how did the cloud fragment at such small masses? Masses well below the theoretical minimum mass for star formation through the ordinary collapse process. McCaffrey himself, speaking to various science media outlets after the publication, was candid about the puzzle. We don't have a satisfying explanation. These objects exist. They are real. And they don't fit neatly into our current theoretical frameworks. That, in science, is exactly the kind of thing that signals that our models are incomplete, and potentially that something genuinely new and important remains to be discovered. The James Webb Space Telescope has transformed our ability to study these objects. Webb's extraordinary infrared sensitivity, combined with its unprecedented spatial resolution, allows it to detect objects far fainter and cooler than any previous telescope could manage. The Orion Nebula findings are almost certainly just the beginning of what Webb will reveal about the population of free-floating planetary mass objects in stellar nurseries across our galaxy. and the implications of those findings for our understanding of planet formation are still being actively worked out. Now let's take a step back from the cutting edge of observation and think about the broader picture of what the population of rogue planets in the Milky Way tells us about the history and dynamics of the galaxy itself. Our galaxy contains hundreds of billions of stars. It has been forming stars for approximately 10 billion years. The Milky Way itself is thought to be about 13.6 billion years old, roughly as old as the universe. Over that enormous span of time, generation after generation of stellar systems has formed, evolved, and sometimes disrupted. Each generation of star formation has produced planetary systems. Those planetary systems have undergone the chaotic, gravitational dynamics of early formation and have ejected planets. Over 13 billion years of this process, the cumulative population of rogue planets, of ejected worlds, of free-floating planetary mass objects formed directly from collapsing clouds, must be enormous. Consider a conservative estimate. If each star system ejects on average just 2 planets during its lifetime, a number that is actually on the lower end of what simulations suggest, then in a galaxy of 300 billion stars, we would have 600 billion rogue planets. That's more than twice the number of stars. And if the ejection rate is higher, if some systems eject 5 or 10 or 20 planets, the total could easily reach into the trillions. The galaxy's dark matter might be a puzzle, but the galaxy's dark planets are a mystery hiding in plain sight, so numerous that they might constitute a significant fraction of the total mass of the Milky Way's disk. Think about that for a moment. When we look out at our galaxy and account for the mass of all the stars, all the gas and dust, all the visible matter, we might be missing a significant contribution from worlds. Dark, cold, wandering worlds, so numerous that they collectively constitute a population larger than the stars themselves, scattered throughout the disk and halo of the Milky Way. Every direction you look in the night sky, there are almost certainly rogue planets passing between us and the distant stars, creating momentary and imperceptible fluctuations in the light we observe. This connects to one of the most fascinating and still actively debated topics in astrophysics: the nature of dark matter. Dark matter is the name given to the mysterious, invisible component of the universe's mass-energy budget that doesn't emit, absorb, or reflect light, but that makes its presence known through its gravitational effects. We know dark matter exists. Its gravitational influence on galaxies, galaxy clusters, and the large-scale structure of the universe is unmistakable and has been confirmed through multiple independent lines of evidence. But we don't know what it is. Proposed candidates have ranged from exotic subatomic particles like WIMPs, weakly interacting massive particles, or axions, to astrophysical objects like black holes and neutron stars. Could some fraction of dark matter be composed of rogue planets? This is a legitimate scientific question, and the answer appears to be probably a small fraction at most. The total mass of rogue planets, even if their numbers are in the trillions, is unlikely to account for more than a few percent of the total dark matter mass budget, because dark matter significantly outmasses all the visible matter in the universe. But the question itself illustrates something important. Rogue planets are not a negligible contribution to the mass-energy inventory of the galaxy. They matter, in the literal gravitational sense, even if they remain invisible. There is also the question of what happens when rogue planets encounter other star systems. Because the galaxy is not empty, stars are not perfectly stationary. There are occasionally close encounters between rogue planets and stellar systems as the galaxy evolves and different regions of the galaxy pass through each other. If a rogue planet passes through a stellar system, the gravitational interactions could have a range of consequences. A very distant encounter might barely perturb anything. A closer encounter might significantly alter the orbits of planets within the system, potentially destabilizing previously stable arrangements. An even closer encounter, though these would be vanishingly rare given the enormous distances between stars, could result in the rogue planet being captured by the stellar system's gravity and becoming a new member of the family it has wandered into, a kind of cosmic adoption. The timescales for these encounters to occur are enormous, millions to billions of years, but given the age of the galaxy, there has been plenty of time for a significant number of them to happen. Some astronomers have proposed that some of the more distant and strangely orbiting bodies in the outer regions of our own solar system, in the region called the Oort cloud and the outer Kuiper belt, might have been acquired through exactly such encounters, or might have their orbits shaped by the gravitational influences of passing stars and, potentially, passing rogue planets. There is even a provocative ongoing hypothesis, sometimes called the Planet 9 hypothesis, that proposes the existence of an as-yet undetected large planet in the far outer solar system, beyond the orbit of Neptune, whose gravitational influence would explain observed clustering in the orbits of extreme trans-Neptunian objects. Some researchers have suggested that if Planet 9 exists, it might actually be a captured rogue planet, a world that once wandered the interstellar void and was eventually captured by the Sun's gravity, becoming the outermost member of our solar system. This remains speculative. Planet 9 itself has not been confirmed, but it is a reminder that the boundary between our solar system and the interstellar medium may be more porous than we typically imagine. Now let's talk about something that is perhaps the most philosophically unsettling aspect of the rogue planet story: what it means for our concept of place in the universe. When we think of Earth, we think of it as embedded in a context. It is the third planet from the Sun. It exists within the habitable zone of a specific, well-characterized star, the Sun, and it has developed the characteristics that make it suitable for life partly because of its position within that system and its relationship with that star. Its liquid water, its relatively stable climate, its protective magnetic field generated by a rotating iron core, its shielding by Jupiter against asteroid and comet bombardment. All of these factors are embedded in a specific context, a specific relationship with a specific star. Now imagine that Earth-like world, with its oceans and its atmosphere and its complex chemistry, being violently expelled from that context. Ejected from the solar system, perhaps billions of years ago, before life had a chance to take hold. What would Earth look like after a billion years of rogue wandering? The oceans would freeze from the surface down. The atmosphere might thin as various gases condensed and froze out. The surface temperature would plummet toward absolute zero. Life on the surface, if there had been any, would perish. But beneath the ice, deep within the crust, near volcanic vents at the bottom of frozen-over oceans, this is not simply a thought experiment. This is a question that scientists are actively exploring. And the answers have implications for how many worlds in the galaxy might harbor, or might have harbored, life, even in the darkest corners of the interstellar medium. Laura Barge, a research scientist at NASA's Jet Propulsion Laboratory who studies the origin of life and conditions for habitability in extreme environments, has pointed out that the conditions needed for the origin of life may not require surface sunlight at all. Her experimental work on simulating hydrothermal vent chemistry in laboratory settings has demonstrated that many of the chemical reactions thought to be involved in the origin of life, the formation of amino acids, the polymerization of organic molecules, the spontaneous formation of membrane-like structures, can proceed in the dark, driven by chemical energy and heat. If the origin of life on Earth itself may have occurred at deep-sea hydrothermal vents rather than at sunlit tide pools, then the argument that life requires sunlight is weaker than it might appear. Consider what this means in the context of rogue planets. A world ejected from its solar system, even if its surface freezes over completely, might still maintain hydrothermal activity in its interior for billions of years. Radioactive decay continues regardless of whether a planet is near a star or wandering between the stars. The interior heat generated by that decay would drive geological activity, volcanism, hydrothermal circulation, for timescales measured in billions of years. If life had already established itself in deep hydrothermal systems before the ejection, it might survive the transition from stellar system to interstellar wanderer. If the chemical conditions for life's origin were met in those deep interior environments, life might even originate on a rogue planet after it has already become a rogue. This is not mainstream consensus science. There are many uncertainties and challenges with this scenario, but it is a scientifically serious idea, explored in peer-reviewed literature, and it represents one of the most genuinely mind-expanding possibilities in modern astrobiology. The idea that the galaxy could be populated not just with worlds orbiting stars, but with entirely independent biospheres existing in the permanent darkness of interstellar space, each one isolated from every other, each one perhaps harboring its own form of chemistry-based life. That idea changes the way you look at the night sky. There is a well-known thought experiment in astronomy called the Fermi paradox, named after the physicist Enrico Fermi, who reportedly asked at a lunchtime discussion in 1950, "Where is everybody?" The Fermi paradox is the apparent contradiction between the high probability estimates for extraterrestrial civilizations and the complete lack of any detected evidence for them. The universe is billions of years old. There are hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have planets. Even if only a tiny fraction of those planets develop life, and even a tinier fraction of that life evolves intelligence, and even a tinier fraction of that intelligence develops technology, the universe should be teeming with technological civilizations, many of them far older than ours. So where is the evidence? Rogue planets potentially add another layer to the Fermi paradox discussion. If civilizations can develop on rogue planets, in the dark, in the deep, sheltered from the catastrophic events that can sterilize star system planets like asteroid impacts, nearby supernovae, and stellar flares, then the potential number of civilizations in the galaxy might be higher than star-centric estimates suggest. But those civilizations would be profoundly isolated, both physically, separated from the nearest stars by light-years of empty space, and informationally, cut off from any cosmic community because the electromagnetic signals that our own civilization has been broadcasting would fade to undetectable levels within a few tens of light-years. A civilization on a rogue planet would have no sun to guide their astronomy, no transits to detect exoplanets, no stellar spectroscopy to study the chemistry of other worlds. Their sky would look nothing like ours. They would see the stars, of course, the galaxy's hundreds of billions of points of light, but no bright, nearby source of light and heat dominating their experience of the cosmos. Their concept of home in the universe would be radically different. Would they even look up? Would they develop concepts of astronomy and cosmology? Or would they turn inward, to geology, to chemistry, to the study of their own interior world, in ways that might make their entire scientific tradition unrecognizable to us? This is pure speculation, of course. We have no evidence of life on any rogue planet. We have no confirmed detection of any rogue planet in detail. All of our detections so far have been through statistical signatures in microlensing surveys, not through imaging or detailed characterization. But speculation grounded in scientific principles is how the scientific frontier is explored, and these questions represent the frontier of the frontier. Now let's talk about what we actually know from observations. The hard data, the confirmed and semi-confirmed discoveries that have given rogue planet science its empirical foundation. Beyond the microlensing surveys, there have been several direct or near-direct detections of rogue planet candidates through infrared imaging. Because young, recently formed rogue planets are still warm from their formation, having not yet had time to radiate away all their primordial heat, they glow in infrared wavelengths bright enough to be detected by sensitive infrared telescopes, particularly when those planets are located in or near star-forming regions where we know young objects will be concentrated. One of the most studied and celebrated of these is an object called CPSR 2149-0403, discovered in 2012 by a team of astronomers including Philippe Delorme using data from the Canada-France-Hawaii telescope and the Very Large Telescope in Chile. This object has a temperature of approximately 700 Kelvin, about 427 degrees Celsius, and a mass estimated at somewhere between 4 and 7 Jupiter masses, placing it in the planet mass to low-mass brown dwarf range, depending on the exact interpretation. It appears to be moving through space as a member of a group of young stars called the AB Doradus Moving Group, suggesting it was formed in the same region and at roughly the same time as those stars, about 50 to 120 million years ago. If its association with that moving group is confirmed, its youth explains its relatively warm temperature. It hasn't had time to cool down. CPSR 2149-0403 is still debated. Some analyses have questioned whether its association with the AB Doradus Moving Group is as clear as initially suggested, but it remains one of the most carefully studied rogue planet candidates. Another prominent example is OTS-44, discovered in 2004. With a mass estimated at approximately 11.5 Jupiter masses, right at the boundary between massive rogue planets and the lowest mass brown dwarfs. OTS-44 is fascinating because it appears to have a disk of gas and dust around it, similar to the circumstellar disks around young stars. The existence of such a disk around a planetary mass object suggests that this object formed the way a star forms, by direct collapse from a gas cloud, and raises the possibility that it could, in principle, have its own planet-forming process occurring around it. Planets forming around a planetary mass object that is itself free-floating. Planets of a rogue planet. The recursion is dizzying. Then there is the remarkable case of PSO J318.5-22, discovered in 2013 by Michael Liu of the University of Hawaii using the Pan-STARRS PS1 telescope. This object, also associated with a young moving group of stars called the Beta Pictoris moving group, has a mass of approximately 6.5 Jupiter masses and a temperature of roughly 1160 Kelvin, quite warm, again reflecting its youth. What made PSO J318.5-22 particularly exciting is that it became one of the best-studied free-floating planetary mass objects because its youth and relatively high temperature made it accessible to spectroscopic study, allowing astronomers to analyze its atmospheric composition in some detail. The spectrum of PSO J318.5-22 shows evidence for dust clouds in its atmosphere, similar to what is seen in the atmospheres of some directly imaged giant exoplanets orbiting young stars. This is a significant finding because it suggests that the atmospheric properties of free-floating planetary mass objects and giant exoplanets are similar, lending credence to the idea that they represent the same class of objects formed by different processes. Each of these discoveries has added a piece to the puzzle. But the puzzle is enormous, and the pieces so far are few. What we need, what astronomers have been working toward for decades, is a systematic, statistically complete survey of the rogue planet population, one that can tell us not just that these objects exist, but how many of them there are, what their mass distribution looks like, what their temperatures and compositions tell us about their origins, and where they are distributed within the galaxy. This is where the future of rogue planet science becomes genuinely thrilling. Because in the coming years, two major observational facilities, the Nancy Grace Roman Space Telescope, formerly known as WFIRST, and the Vera Rubin Observatory, are expected to transform our knowledge of rogue planets in ways that are almost difficult to imagine. The Nancy Grace Roman Space Telescope, named in honor of NASA's first chief of astronomy, is a next-generation space telescope with a primary mirror as large as the Hubble Space Telescopes but with a field of view 100 times wider. One of Roman's core science programs is a microlensing survey of the galactic bulge, specifically designed to detect the brief, characteristic microlensing signatures of Earth-mass free-floating planets. Current microlensing surveys like OGLE are largely sensitive to Jupiter-mass rogue planets. The events caused by smaller Earth-mass objects are too brief and too faint to reliably detect from the ground with current technology. Roman, with its space-based precision and wide-field infrared camera, is expected to detect events lasting less than an hour, the kinds of events that would be produced by Earth-mass and even Mars-mass rogue planets. The predictions for Roman's yield are extraordinary. Over its 5-year primary mission, Roman could detect thousands of rogue planet microlensing events, transforming the field from a collection of intriguing but individually uncertain detections into a statistically robust population study. The Vera Rubin Observatory, sited on Cerro Pachón in Chile and scheduled to begin full science operations in the mid-2020s, will conduct a 10-year survey of the entire southern sky called the Legacy Survey of Space and Time, or LSST. While Rubin's primary sensitivity is in visible light rather than infrared, and it is less optimized for microlensing of galactic bulge targets than Roman, its extraordinary breadth of sky coverage means it will nonetheless detect large numbers of microlensing events, including some caused by rogue planets, and will also be sensitive to young, warm rogue planets detectable through their direct emission in certain optical wavelengths. Together, Roman and Rubin could give us, within the next decade, a fundamentally transformed picture of the rogue planet population of the Milky Way. The question of how many rogue planets there are per star in the galaxy, currently constrained to rough order of magnitude estimates, could be answered with actual statistical precision. The question of whether the mass distribution of rogue planets follows what we would expect from planetary system formation models or deviates from those predictions in ways that suggest a significant population of directly formed planetary mass objects, could be addressed with real data. This matters enormously for understanding where planets come from. If the rogue planet population is consistent with what planetary system formation models predict from ejection alone, we can breathe a sigh of satisfaction that our models are approximately right. But if there is a large excess of rogue planets relative to those predictions, if the numbers are so high that ejection from stellar systems can't explain them all, it implies that there is a significant population of directly formed planetary mass objects, which in turn implies that the process of star formation produces objects across a much wider range of masses than our current models fully explain. It would mean that the boundary between star formation and planet formation is blurrier than we thought, that the universe makes planet-sized things by two entirely different mechanisms, and that both mechanisms are common. This has implications beyond just the counting of worlds. It affects our understanding of the initial mass function, the distribution of masses with which stars and stellar-like objects form, and by extension it touches on fundamental questions about the physics of turbulence, fragmentation, and gravity in the interstellar medium. These are not arcane technical details. They are core questions about how the universe organizes matter on the largest scales. While we wait for those future observatories to transform the field, let us turn to something that has been lurking at the edges of the story and that deserves its own careful treatment. The story of a real object, possibly a rogue planet, that may have already visited our solar system. In October 2017, astronomers working with the Pan-STARRS telescope in Hawaii detected an object moving through the inner solar system on a trajectory that was unambiguously hyperbolic, meaning it was moving too fast to be bound by the sun's gravity and would pass through our solar system and escape into interstellar space, never to return. This was an extraordinary discovery. Every other small body in the solar system, every comet, every asteroid, moves on an elliptical orbit bound by the sun's gravity. This object was different. It had come from interstellar space, and it was passing through. It was given the designation 1I/2017 U1 and the name Oumuamua, a Hawaiian word meaning something like a messenger from afar arriving first, a poetic and apt name for the first confirmed interstellar object ever observed passing through the solar system. Now, Oumuamua was not a rogue planet. It was far too small for that, estimated to be only a few hundred meters across at most. But it demonstrated something that had previously only been theorized, that interstellar objects do pass through stellar systems. And if a small interstellar body, a fragment, a remnant, passes through our solar system, then rogue planets, far more massive, are certainly drifting through the same volume of space, invisible to us but present nonetheless. Oumuamua became one of the most intensely studied and bitterly debated objects in the history of solar system astronomy. Its trajectory was bizarre. As it moved away from the sun, it appeared to be accelerating slightly more than gravity alone could account for, a so-called non-gravitational acceleration. For comets, this is normal. Jets of gas and dust sublimating from the surface as the comet warms near the sun create a rocket-like push that slightly alters the trajectory. But astronomers found no evidence of any cometary activity from Oumuamua. No coma, no dust trail, no gas emission detectable by any telescope. Whatever was causing the extra push, it wasn't standard cometary outgassing. The explanations proposed were numerous and sometimes colorful. Some researchers suggested it might be outgassing of molecular hydrogen ice, which would be undetectable by current instruments but could explain the acceleration. Others proposed it might be a dust trap, a highly porous, almost foam-like object, whose unusual structure somehow mimicked the effect. And then there was the suggestion by Avi Loeb, a Harvard astrophysicist of considerable prominence, who proposed, with calculation and supporting argument, that Oumuamua's properties were most easily explained if it were an artificial object, a light sail, perhaps, of extraterrestrial technological origin. Loeb wrote an entire book on the subject, Extraterrestrial, the first sign of intelligent life beyond Earth, published in 2021, in which he argued that the scientific establishment was too quick to dismiss the possibility of artificial origin without fully engaging with the evidence. Loeb's proposal was met with deep skepticism from the majority of the astronomical community. who felt that the extraordinary nature of the hypothesis required extraordinary evidence that was simply not present. Most researchers favor natural explanations, and subsequent papers have offered viable natural mechanisms for Oumuamua's anomalous acceleration. But the episode illustrated something important. The detection of interstellar objects, whether natural or not, is no longer purely theoretical. It happens, and it will happen again. In 2019, just 2 years after Oumuamua, a second interstellar object was detected, 2I/Borisov, discovered by amateur astronomer Gennady Borisov. Borisov behaved much more like a conventional comet. It showed clear cometary activity, had a visible coma, and its trajectory, while hyperbolic, was otherwise unremarkable. It was clearly a fragment of some distant planetary system, a comet flung outward by whatever gravitational dynamics governed its home system and sent tumbling through the interstellar medium until it chanced to pass through ours. Its detection confirmed that Oumuamua was not a one-off freak event. Interstellar objects are passing through our solar system regularly. Models suggest that at any given time, there may be several such objects within the inner solar system, too faint to detect with current technology. This raises a tantalizing question. Could fragments of rogue planets, or actual rogue planet encounters, leave detectable traces in the solar system? Could some of the most distant and strangely orbiting objects in the outer solar system, in the Oort cloud, that vast spherical shell of icy bodies thought to surround the solar system at distances of tens of thousands to hundreds of thousands of astronomical units, have been captured from interstellar space? Could the Oort cloud itself have been partially seeded by material from other stellar systems, including perhaps from rogue planet collisions and disintegrations in the interstellar medium? These are genuinely open questions, and answering them would tell us something profound about the interconnectedness of planetary systems across the galaxy, about whether our solar system is truly isolated or whether it has been exchanging material with other systems for billions of years, making the Milky Way a kind of slow, vast commons of planetary debris and wandering worlds. Let us pause here and consider the emotional dimension of this story. Not just the scientific facts, but what they mean for how we experience our place in the universe. There is something profoundly moving about the image of a rogue planet. A world, perhaps once warm, perhaps once young and active with geology and chemistry, expelled from its home into the darkness, traveling alone, in silence, through the immensity of interstellar space, cooling slowly over billions of years. Its surface freezing, its sky growing darker as it leaves behind the last vestiges of stellar warmth. And then, if the models allow it, perhaps deep inside its frozen shell, beneath kilometers of ice, in the darkness of some internal ocean warmed by the last whispers of radioactive decay, something small and chemical and complex persisting. Something that, in the most generous interpretation of what we mean by the word, might be called alive. The philosopher Thomas Nagel famously asked what it is like to be a bat, pointing out that there is a subjective experience of being a bat that we can never fully access from the outside. We can study bat anatomy and echolocation and behavior in complete detail and still never know what it actually feels like from the inside to navigate the world by sound in the dark. What is it like to be a world? That is not a scientific question, but it is a question that the story of rogue planets invites us to ask in a new way. What is it like to be a world that once had a sun and no longer does? What does a world lose when it loses its star? The answer, in the physical sense, is enormous. The star is the source of almost all the energy that drives a world's surface processes. It drives the water cycle, the atmospheric circulation, the photosynthetic processes of life. It provides the ultraviolet radiation that creates ozone layers that shield surfaces from cosmic rays. It provides the solar wind that interacts with a planet's magnetic field in complex and sometimes beautiful ways, causing auroras, shaping the magnetosphere, carrying information about the star's activity to the planet's environment. All of that ends when a planet is ejected. The loss is total and irreversible. But the interior remains. The heat remains for a while, for billions of years if the planet is large enough. The chemistry remains. The possibility of certain kinds of process remains deep in the dark interior, for timescales that overlap with the timescales of biological evolution on Earth. And that is enough, perhaps, to keep a story alive. A story of molecules combining and reacting and building complexity. Long after the star that once illuminated the beginning of that story has faded to a distant, indifferent point of light. We should also talk about the possibility that rogue planets could play a role in spreading life across the galaxy. An idea that goes by the technical term panspermia, and in the case of rogue planets, specifically lithopanspermia, the transport of life within rocky fragments. The idea of panspermia, that life is not confined to the world where it originates, but can be transported from world to world within the same system or even between different systems, has a long history in scientific discussion. Within our own solar system, there is genuine evidence that material is exchanged between planets. The Mars meteorites found on Earth are literal fragments of the Martian surface, blasted into space by asteroid impacts and eventually captured by Earth's gravity. If Mars ever had life, those meteorites might, in principle, have carried it to Earth. Similarly, Earth material has almost certainly reached Mars, though in smaller quantities. But interstellar panspermia, the transport of life between star systems, or from a rogue planet to a stellar system, or from a stellar system to a rogue planet, involves distances and timescales that strain the limits of what microorganisms can survive. The distances between stars are measured in light years. Even at the typical velocities of interstellar objects, the travel time between star systems is measured in millions to tens of millions of years. Can any microorganism survive that long in the cold and radiation of interstellar space? The answer is, probably not without significant protection. Bare spores exposed to cosmic radiation in interstellar space would accumulate lethal radiation damage over thousands to millions of years. But if they are embedded deep inside a large rock, a meter or more of rock would provide substantial shielding against cosmic rays. The survival time extends considerably. Some of the hardiest microorganisms known to science, including certain bacteria and archaea, can survive extraordinarily hostile conditions through a combination of dormancy, radiation-resistant DNA repair mechanisms, and extreme structural robustness. Deinococcus radiodurans, famously known as the world's most radiation-resistant organism, can survive radiation doses that would kill a human thousands of times over. Some organisms can survive in frozen states for millions of years. The 2021 discovery of microorganisms revived from 100-million-year-old marine sediments from the South Pacific was a genuine scientific sensation, though the claim is debated. Could rogue planets facilitate panspermia? A rogue planet that passes through a stellar system, even at relatively high velocity, might exchange surface material with the planets of that system through a complex series of gravitational interactions and impact events. A fragment of the rogue planet's surface, blasted off by an impact, might be captured by the stellar system's gravity and eventually deliver its cargo, including any microorganisms embedded within it, to a habitable world within that system. Conversely, material from a habitable world in a stellar system might end up on a passing rogue planet. These scenarios are extremely improbable for any individual encounter. But the galaxy is very old, and the numbers of rogue planets are potentially enormous, and the timescales available for such exchanges are measured in billions of years. In a statistical sense, even extremely improbable events become nearly inevitable over sufficient time and scale. Some researchers have taken seriously the idea that if life began once in the galaxy, anywhere, it might have had billions of years to spread to other worlds through exactly such mechanisms, including through the medium of rogue planets acting as interstellar stepping stones in the dark. This is a theory, and it is speculative. The evidence for it is largely indirect and statistical, but it represents one of the most genuinely exciting frontiers in astrobiology. The possibility that life in the universe might be not just widespread but interconnected, spread by the same physical processes that move matter around the galaxy. Let's think now about what it might be like to actually try to study a rogue planet up close. Not just statistically, not just through the indirect signatures of microlensing, but in detail, the way we have studied the planets of our own solar system. The challenge is enormous. Even the closest rogue planet to Earth, whatever it is, is almost certainly many light years away. The nearest known star system, Alpha Centauri, is about 4.2 light years from Earth. Any rogue planets in the immediate solar neighborhood would be at distances of similar magnitude, measured in light years. With current chemical rocket technology, a spacecraft launched from Earth today would take tens of thousands of years to travel even a single light year. Even with the most optimistic proposed propulsion technologies, nuclear pulse drives, laser light sails of the kind proposed by the Breakthrough Starshot initiative, reaching a target several light years away within a human lifetime is barely conceivable, and the challenges of communication and data return over such distances are formidable. But there are intermediate steps, and they are being actively discussed. If a rogue planet were to pass close enough to the solar system, within, say, a few hundred astronomical units, which would be within the outer Oort cloud, it would be much more accessible. And such a passage might not be as rare as it sounds. Statistical estimates suggest that rogue planets pass within a few hundred AU of the Sun on timescales of perhaps millions of years. We have no way to detect such a passage in advance with current technology, because rogue planets are dark and cold and essentially invisible until they are very close. But a next-generation deep space infrared telescope or a dense network of outer solar system monitoring probes might be able to detect an approaching rogue planet with enough warning to contemplate a mission. The idea of a fast response mission to an interstellar object, like Oumuamua, has been seriously discussed in the context of space agency mission planning. A concept study called Project Lyra, proposed by members of the Initiative for Interstellar Studies, examined what it would have taken to send a spacecraft to intercept Oumuamua, and concluded that it would have been possible, though challenging, using Jupiter gravity assist maneuvers to achieve the high velocities needed. A similar approach applied to a rogue planet passing through the outer solar system, if detected far enough in advance, could, in principle, allow a spacecraft to intercept and study it in some detail. Not land on it, not orbit it for years, but fly past it quickly and collect data. Such a flyby would be an extraordinary scientific event. Imagine the data: thermal profiles of the surface and interior, compositional information from spectroscopy, imaging of geological features, detection of any atmospheric gases, measurements of the magnetic field, perhaps even searches for biosignatures, chemical signatures of life, in the spectra of any gases or surface features. It would be, in a modest but real sense, the first close encounter between human exploration and the interstellar realm, the first time we had actually reached out and touched something that came from between the stars. The technological challenges are not trivial, but they are engineering challenges, not physics challenges. There is no known law of physics that prohibits a fast flyby of an interstellar object transiting through the outer solar system. The question is one of detection, preparation, and political will to fund and execute such a mission on short notice, likely within a few years of detection. These are hard practical problems, but they are the kinds of hard practical problems that the space exploration community has shown itself capable of solving when the scientific and political will exists. Now let us turn to some of the more dramatic implications of rogue planets for the fate of our own solar system, and by extension for the long-term future of Earth. The Sun is not eternal. Like all stars, it will go through an evolutionary sequence that will eventually make it uninhabitable for any Earth-based life. Approximately 5 billion years from now, the Sun will exhaust the hydrogen fuel in its core and begin fusing hydrogen in a shell around the core, causing it to expand into a red giant star. During this red giant phase, the Sun's outer atmosphere will swell enormously, perhaps reaching out to the orbit of Earth, possibly beyond. The inner solar system will be rendered uninhabitable. Earth, if it still exists, and there is genuine uncertainty about whether Earth will be engulfed or merely scorched, will be sterilized by the Sun's enormously increased luminosity long before the red giant phase is fully reached. This is a fact, not speculation. It is a consequence of well-understood stellar physics. The death of the Sun as a habitable star is as certain as any physical prediction can be, though it lies billions of years in the future. Viewed on cosmological timescales, the Sun's habitable phase is finite, and it is more than half over. But what happens to our solar system after the Sun's red giant phase? The Sun will eventually shed its outer layers in a planetary nebula, leaving behind a dense, white dwarf star, an Earth-sized ball of compressed carbon and oxygen, slowly cooling over billions of years. The outer planets, Jupiter, Saturn, Uranus, Neptune, will survive as they are, their orbits shifted outward by the mass loss from the Sun, but otherwise structurally intact. And it is not impossible that in the far future, tens of billions of years hence, some of those outer planets might themselves become effectively detached from the solar system's gravitational grip through close encounters with other stars, becoming rogue planets themselves. On timescales comparable to the age of the universe, the fate of every planetary system is ultimately dispersal. Stellar encounters, galactic tidal forces, and the decay of gravitational binding energy through radiation ensure that even tightly bound systems will eventually lose their members. The end point for every planet, in the longest view, is the interstellar void. Every planet is eventually a rogue planet. Earth's current situation, orbiting in a habitable zone, warmed by a benevolent star, home to a complex biosphere, is a temporary condition in a universe that trends, inexorably, toward cold and darkness. This is not a counsel of despair. It is simply the truth about the universe as we understand it. And there is something clarifying and even beautiful about confronting it. The warmth and light and life on Earth are not permanent features of the universe. They are a specific, precious, temporary arrangement of matter and energy in a specific corner of a specific galaxy, and they are, on the scale of cosmological time, ephemeral. The rogue planets remind us of this. They are the afterimages of stellar systems, the remnants of conditions that once existed and no longer do. They are the cosmic record of worlds that were once embedded in light and heat and are now alone in the dark. There is a body of research that explores what the universe will look like in the far future, trillions and quadrillions of years from now, as stars exhaust their fuel and galaxies fade and the cosmos grows cold and dark. This field, sometimes called physical eschatology, was famously systematized by Fred Adams and Gregory Laughlin in their 1999 book, The 5 Ages of the Universe, which laid out a timeline of cosmic evolution from the current stelliferous era, the age of stars, through the degenerate era, the black hole era, and the dark era, where even protons have decayed and the universe is a cold, diffuse mist of photons and leptons cooling toward absolute zero. In that far future, rogue planets, or rather the frozen remnants of rogue planets, will be among the last complex structures in the universe. Stars will have burned out. Black holes will have evaporated through Hawking radiation. But a rocky or icy world, once frozen solid, faces no obvious decay mechanism on timescales shorter than the proton lifetime, which, if protons decay at all, and whether they do is still an open question in physics, is estimated to be at least 10 to the 33rd years, an incomprehensibly large number compared to the current age of the universe of approximately 14 billion years. A rogue planet could persist, frozen and dark, for timescales that make the current age of the universe look like the blink of an eye. In the deepest future, rogue planets might be among the only surviving records of the stelliferous era. Frozen testimonials to the age when stars burned and worlds were warm and complex processes of chemistry and perhaps biology were possible. In a universe grown cold and dark, these frozen wanderers would carry the memory of complexity in their frozen chemistry, in the crystalline structure of their frozen oceans, in the preserved geology of their interiors. They would be, in a sense, the last libraries of the stelliferous age, archives of a time when the universe was alive with light. This is, of course, speculation carried to its extreme, and none of us will be around to verify it. But it gives the story of rogue planets a dimension that extends far beyond the immediate questions of how they form or whether they might harbor life. It places them in the full context of cosmic evolution, not as curiosities or anomalies, but as a fundamental and in some ways culminating feature of the universe's long arc from hot and bright to cold and dark. Let us return now to the more immediate present, and to some of the most fascinating and recent developments in rogue planet science that are unfolding right now as the story is being told. The year 2023 was a landmark year for the study of free-floating planetary mass objects, primarily because of the James Webb Space Telescope's first deep looks into stellar nurseries. The Orion Nebula results that we mentioned earlier, the jumbos, were published in late 2023 and generated a wave of commentary and discussion among astronomers worldwide. The fact that so many planetary mass objects appear to exist in the Orion Nebula in binary pairs was a shock to the theoretical community, because none of the existing models of planet formation or star formation easily produced such objects. Samuel Pearson, a research scientist at the European Space Agency and one of the lead authors of the Jumbo study, was quoted in multiple science journalism outlets as saying that the results were something of a mystery. His collaborator Mark McCaffrian, also a prominent ESA scientist and Webb interdisciplinary scientist, was similarly candid about the difficulty of explaining the observations within current theoretical frameworks. The Webb telescope's extraordinary sensitivity had opened a new observational window, and immediately revealed that what was in that window was more complex and more surprising than anyone had predicted. The astronomical community's response was rapid. Within months, multiple theoretical papers appeared proposing various mechanisms that might explain the jumbos, including the possibility that they formed in protoplanetary disks around young stars and were subsequently dynamically ejected as binary pairs through complex three-body interactions. A scenario that, while statistically unlikely in individual cases, might be plausible given the dense stellar environment of a young star cluster like the Orion Nebula, where close stellar encounters are relatively frequent. Other papers proposed that the jumbos formed directly through a turbulence-driven fragmentation process in the nebula itself, at mass scales well below what conventional star formation models predict, suggesting that the minimum mass for star formation through gravitational collapse is lower than previously thought. The resolution to the jumbo mystery is not yet clear. It might require years of additional observation and theoretical development to resolve. But it is a reminder that nature is consistently more inventive than our models, and that the universe has more ways of making things than we have yet imagined. Meanwhile, microlensing surveys continue to accumulate data. The KMT-NET, Korea Microlensing Telescope Network survey, which uses 3 identical 1.6-meter telescopes distributed across South Africa, Chile, and Australia to monitor the galactic bulge continuously with no gaps caused by Earth's rotation, has been producing a rich stream of microlensing detections. Statistical analyses of KMT-NET data are providing ever more refined estimates of the frequency of short-duration microlensing events, the telltale signatures of low-mass free-floating objects. As these analyses accumulate, they are building toward a statistically robust measurement of the mass function of the rogue planet population, which will eventually be the cornerstone observational constraint for models of planetary system formation and evolution. There is also exciting work being done to combine microlensing observations with other data. The Gaia Space Astrometry mission, operated by the European Space Agency and producing extraordinarily precise positional measurements of over 1 billion stars, is in principle sensitive to astrometric microlensing, the tiny apparent shifts in a star's position caused by the gravitational lensing effect of a passing body, rather than the brightening of photometric lensing. Combining Gaia astrometric microlensing data with photometric microlensing from ground-based surveys has the potential to provide mass measurements of the lensing objects without the ambiguity that plagues photometric-only events, where the lens mass is typically highly uncertain. This is technical and detailed work, but the scientific payoff is potentially immense. For the first time, we might be able to not just detect rogue planet events, but actually measure the masses of the lensing objects with meaningful precision, giving us a real mass distribution for the rogue planet population rather than rough statistical estimates. We should also spend some time talking about what happens to the atmospheres and surfaces of rogue planets over geological time, because the long-term evolution of a rogue world is profoundly different from that of a planet in a stellar system, and some of the differences are counterintuitive. One of the most important threats to planetary atmospheres and stellar systems is the stellar wind, the continuous stream of charged particles emitted by a star. The solar wind is responsible for the gradual stripping of Mars's atmosphere over billions of years, a process that turned a world that may once have had liquid water and a thick atmosphere into the thin, cold, radiation-exposed place it is today. On Earth, the magnetic field protects us from solar wind stripping, but even Earth loses small amounts of atmosphere continuously. A planet without a strong magnetic field in a stellar system will gradually lose its atmosphere to stellar wind erosion, especially for light gases like hydrogen and helium. A rogue planet faces no stellar wind. The interstellar medium through which it travels is orders of magnitude less dense and energetic than the stellar wind at the distances typical of habitable zone planets. This means that a rogue planet with a thick atmosphere might actually be able to retain that atmosphere far more effectively than a comparable planet in a stellar system. The hydrogen atmosphere proposed by Stephenson's theoretical work as a mechanism for rogue planet warming might be able to survive for billions of years on a rogue planet, whereas such an atmosphere on an Earth-like planet within a habitable zone might be rapidly stripped by the host star's radiation and wind. This is a genuinely important point. If thick hydrogen atmospheres are the key to maintaining liquid water on rogue planets, and if those atmospheres can be retained far better in the absence of a star's energetic output, then the longevity of potentially habitable conditions on rogue planets might actually exceed that of comparable planets in stellar habitable zones. Earth's habitable conditions will last only as long as the Sun remains in its main sequence phase, another 5 billion years or so. A rogue planet with a thick hydrogen atmosphere might maintain its internal heat and liquid subsurface water for even longer, depending on its mass and initial radioactive element content. Cosmic rays are another environmental factor worth considering. The interstellar medium is permeated by cosmic rays, high-energy charged particles, mostly protons and heavy nuclei accelerated to near light speed by supernovae and other energetic astrophysical events. On Earth, cosmic rays are largely deflected by the magnetic field and absorbed by the atmosphere. The small fraction that reach the surface contribute to things like mutation rates in DNA and the formation of certain chemical species. On a rogue planet in interstellar space, the surface would be exposed to whatever cosmic ray flux the planet's magnetic field and atmosphere didn't deflect or absorb. If the planet had a thick hydrogen atmosphere, much of the cosmic ray flux would be absorbed before reaching the surface. The subsurface environment would be even better shielded. So for subsurface life, if such a thing exists, the cosmic ray environment of interstellar space might be less of a threat than it initially appears. Ultraviolet radiation from nearby stars is another concern in stellar systems. UV drives photochemistry in atmospheres, including the creation of protective ozone layers, but also can damage biological molecules near surfaces. In the deep interstellar medium, far from any star, the UV flux is essentially zero. This is a mixed blessing. There is no UV-driven photochemistry to create ozone or other protective molecules, but there is also no UV radiation to damage anything. The environment below the surface of a rogue planet, inside its frozen shell, in any internal ocean, would be extraordinarily well shielded from all forms of harmful radiation, making it one of the more radiation-benign environments we can imagine for the sustenance of life. Now let's think about some of the speculative scenarios that push our understanding to its limits, the kinds of ideas that serious scientists think about but that push right up to and sometimes past the boundary of mainstream scientific consensus. One intriguing speculative scenario involves the possibility that a rogue planet could be artificially inhabited, modified by a technological civilization to serve as a kind of generation ship for interstellar travel. The idea is not as outlandish as it might initially seem. Rogue planets are, by definition, already in interstellar space, already traveling between star systems. A technological civilization with sufficiently advanced capability might see a large rogue planet not as a problem but as an opportunity. A built-in interstellar vehicle, massive enough to provide significant gravity and shielding, with internal heat sources that could potentially be exploited or supplemented. The civilization would need to somehow generate sufficient energy for life support, perhaps through advanced nuclear technology, perhaps through the exploitation of the planet's own geothermal energy, and would need to manage the atmospheric environment. But in principle, a rogue planet is a more viable generation ship than any spacecraft we have conceived of, by virtue of its sheer size and the shelter its mass provides. This idea appears in science fiction. Kim Stanley Robinson's novel Aurora deals with a generation ship traveling between stars, and various other works of speculative fiction have explored the idea of rogue planets as mobile habitats or spacecraft, but it has also been briefly discussed in serious scientific and technological futurist contexts. It is speculative, to be clear. We have no evidence that any civilization has done this or is currently doing this. But the scenario has a beautiful internal logic that makes it worth thinking about. the universe's dark, wandering worlds as the interstellar vessels of civilizations advanced enough to use them. There is a related speculation, even further from mainstream science, and properly labeled as highly speculative, that the anomalous acceleration of Oumuamua might be related to the possibility that interstellar objects in general, including rogue planets, sometimes bear the marks of civilizational activity. This is Avi Loeb's territory, and while his specific proposals about Oumuamua are not widely accepted by the mainstream community, the broader question, could advanced civilizations have left detectably anomalous objects in the interstellar medium, is one that a few researchers take seriously in the context of technosignature searches. If a rogue planet were found with anomalous properties, unusual surface features visible in infrared, unexplained spectroscopic signatures, non-gravitational dynamical behavior, those would be appropriate things to investigate carefully before attributing to natural causes. This is not an argument that alien artifacts are lurking in the interstellar medium. It is simply a recognition that the principle of thorough investigation before conclusion is the correct one, and that the interstellar realm is vast and poorly surveyed. Let's pivot now to some of the human stories embedded in the science of rogue planets. The scientists who have dedicated their careers to studying these objects, the moments of discovery that have shaped the field, and the institutional and cultural factors that have influenced how rogue planet science has developed. The field of rogue planet science is relatively young. While the theoretical prediction of planet ejection from early planetary systems goes back several decades in planetary dynamics research, the observational study of free-floating planetary mass objects began in earnest only in the late 1990s and early 2000s, when a combination of advances in infrared detector technology and the maturation of the microlensing technique made it possible to actually find these objects rather than just predict them. The Microlensing Observations in Astrophysics Survey (MOA) was one of the pioneering collaborations in this space, and the 2011 paper by Takahiro Sumi and collaborators representing the MOA team was a defining moment in the field. The Nature publication was accompanied by significant media attention, and the idea of hundreds of billions of Jupiter-mass rogue planets caught the public imagination in a way that more technical papers rarely do. The image of a dark Jupiter wandering alone between the stars is inherently cinematic, and science journalists made the most of it. But the road from that 2011 paper to the current state of the field has not been entirely smooth. The statistical methodology used to derive the rogue planet population estimate from MOA data has been the subject of ongoing debate and refinement. Subsequent analyses, including a 2017 reanalysis of the MOA data by Przemek Mraz and collaborators using the OGLE survey, found fewer short timescale events than the original 2011 analysis, suggesting that the number of Jupiter-mass rogue planets per star might be lower than originally estimated, perhaps closer to 1 per star rather than 2. But the same analysis found evidence for an abundant population of Earth-mass rogue planets, objects inferred from even shorter timescale events, suggesting that while the Jupiter mass population might be more modest than originally thought, the overall rogue planet population could still be enormous, dominated by smaller, harder-to-detect objects. This kind of revision and refinement is completely normal in science, and is a sign of a field working as it should. The initial dramatic claim attracts attention and resources. Subsequent analysis sharpens and sometimes modifies the initial result. The field converges toward a better understanding over time. The history of the rogue planet field illustrates this process clearly. The involvement of young researchers and graduate students in rogue planet science has also been notable. Because the field is relatively new and relatively open, there's a great deal of territory still to be mapped. It is in many ways an ideal field for young scientists who want to work on genuinely open questions without spending decades paying dues in a fully mature field. Several of the key papers in rogue planet science have been led by early career researchers, and the field has a collaborative and somewhat adventurous culture that reflects its frontier character. The international character of rogue planet research is also worth noting. Major contributions have come from research groups in Japan, New Zealand, Poland, France, the United States, South Korea, Chile, and beyond. The microlensing surveys that have been the backbone of rogue planet statistics involve large international collaborations, MOA, OGLE, KMTNet, that are models of scientific cooperation, combining the complementary resources and expertise of multiple nations to tackle a problem that no single country could address alone. This international character reflects both the scientific scale of the challenge and the genuine global interest in understanding these wandering worlds. Now, let's look at the rogue planet question from a different angle entirely. Not from the perspective of the scientists studying them, but from the perspective of what they mean for the way we tell stories about the universe. Human cultures across history have used the night sky as a canvas for narrative and meaning. The stars have been characters in myths, guides for navigation, markers of seasons, objects of worship, symbols of constancy and eternity. The very word planet comes from the ancient Greek planets, meaning wanderer, because the planets, visible with the naked eye as points of light that moved against the fixed backdrop of stars, were the wanderers of the ancient sky. Mars, Venus, Jupiter, Saturn, Mercury. These were the gods who walked among the fixed stars, whose movements were tracked and interpreted and incorporated into the stories cultures told about themselves and their place in the cosmos. Now we have discovered a new class of wanderers. Wanderers that don't even have a sky, that carry no light, that are known to us only through the momentary flicker of borrowed light and the mathematical inference of gravitational influence. These are the rogue planets, and they are wanderers in a sense far more profound than the ancient Greeks could have imagined. Not merely moving against a backdrop of stars, but moving between the stars themselves, in the void that separates one stellar family from another, in the darkness that separates one island of light from the next. There is a poetic resonance to the idea of rogue planets that connects to deep human themes: exile, isolation, the loss of community and warmth, the journey without destination. These are themes that appear in the mythologies of cultures around the world, and they appear in the rogue planet story in a strikingly literal way. These are worlds that have been exiled from their star systems, that have lost the warmth and light that defined their early existence, that wander without destination or purpose in the cosmic dark. If we are tempted to anthropomorphize them, to feel something when we contemplate their solitude, that impulse is not purely sentimental. It reflects a recognition that the rogue planet story is, in some abstract and impersonal way, a story about loss and endurance. And those are stories that human beings know how to hear. Ask yourself this: if you discovered that there was a world out there in the darkness, carrying a frozen ocean and the chemical residue of processes that might, in the most generous reading, constitute something like life, would you want to know? And if you would want to know, what would it mean to find out? What would it mean for how you think about the universe, about life, about the nature of home? These are not rhetorical questions. They are questions that are beginning to be asked in the halls of major research universities and in the strategy documents of major space agencies, as the tools needed to begin answering them gradually come online. Let us now explore one of the most dramatic specific scenarios involving rogue planets. What would happen if one were to pass through the inner solar system, close enough to interact gravitationally with Earth's orbit? This is a scenario that scientists have modeled in some detail. The probability of a rogue planet passing close enough to the inner solar system to significantly affect Earth's orbit on any given human timescale is extraordinarily small. We're talking about events that might happen on timescales of billions to tens of billions of years for close encounters. The average distance between stars in the Milky Way is several light years, and the inner solar system is tiny compared to those distances. So a rogue planet traveling at typical interstellar velocities of several tens of kilometers per second would be extremely unlikely to pass through or near the inner solar system. But extremely unlikely does not mean impossible. And on the timescales of the universe's history, improbable events do occasionally occur. Computer simulations of close stellar encounters where a star or rogue planet passes within a few thousand astronomical units of the Sun, have been run by researchers including Corinne Baylor-Jones at the Max Planck Institute for Astronomy, who has systematically identified close stellar approaches to the Sun using Gaia data. While no confirmed rogue planet approaches are known for the near future, the catalog of known stellar approaches tells us something about the frequency and character of such events, and rogue planet approaches are expected to occur on similar timescales. A rogue planet passing through the outer solar system, through the Oort cloud region, would gravitationally perturb the orbits of countless comets and icy bodies in that region, potentially sending showers of comets into the inner solar system over the following hundreds of thousands of years. Such comet showers have been proposed as an explanation for some of the major mass extinction events in Earth's history, including potentially the Permian-Triassic extinction event 252 million years ago, which wiped out more than 90% of marine species and more than 70% of terrestrial vertebrate species, the largest mass extinction in Earth's history. Whether a rogue planet could have been responsible for sending the comet showers that some researchers have proposed as contributing to these events is speculative, but it is a hypothesis that has been discussed in the scientific literature. A rogue planet passing much closer, within the inner solar system, would be a catastrophic event for Earth. The gravitational perturbation of Earth's orbit could be severe, potentially disrupting the stable, nearly circular orbit that contributes to Earth's relatively stable climate and ejecting Earth from the solar system in the same way that rogue planets themselves are created. This is, to be absolutely clear, an event of vanishingly small probability on any human timescale, and there is no known rogue planet on a collision course with the solar system. But it is a reminder that the universe is not permanently obligated to be benign, and that the comfortable stability of our current situation is something to appreciate rather than take for granted. There is something almost recursive about this scenario. The same gravitational dynamics that create rogue planets by ejecting them from stellar systems could, in principle, acting through a rogue planet encounter, eject Earth from our solar system. Earth could become a rogue planet. The possibility is real in principle, though vanishingly unlikely on any human time frame. Let's think about what Earth would look like as a rogue planet. Immediately after ejection, assuming a relatively slow ejection that allowed the biosphere time to respond, the most obvious change would be the gradual dimming and disappearance of the Sun. Over years to decades, the Sun would fade from the brilliant star that dominates our sky to a bright point of light, to a faint point, and eventually to invisibility below the threshold of the naked eye. Surface temperatures would plummet. The oceans would begin to freeze from the surface down, slowly at first, then more rapidly as the ice cover grew and reflected more incoming energy. Photosynthesis would fail as light levels dropped below the minimum needed by plants and algae. The food webs dependent on photosynthesis would collapse within years to decades. But the story wouldn't end there. Beneath the ice, which would grow to kilometers in depth over millions of years, the oceans would remain liquid for a while, warmed by Earth's internal heat. The deep-sea hydrothermal vent communities would survive, potentially for billions of years. The surface would become a frozen wasteland of extraordinary severity, but deep below, in the darkness of a frozen-over ocean, the chemistry of life might persist. Bacteria and archaea in the deep subsurface, protected by kilometers of rock from radiation and insulated from the cold by the overlying geology, would likely survive for very long timescales, potentially indefinitely given ongoing geothermal heating. Humanity, of course, would face an existential crisis. The failure of photosynthesis and the collapse of surface food webs would make the surface of a rogue Earth uninhabitable for complex life within decades. Our only hope would be to retreat underground or into sealed habitats with artificial light sources and controlled ecosystems, essentially becoming a civilization of the interior, powered by geothermal energy and nuclear fission or fusion, farming in the dark like the deep-sea organisms that were always there. It is a scenario that science fiction has explored. The Polish writer Stanislaw Lem contemplated variations on it, and more recently Charlie Jane Anders explored similar territory. And it is a scenario that focuses the mind wonderfully on the question of what human civilization ultimately requires. Warmth, yes, and energy, yes, but not necessarily a sun. Not necessarily this sun. Now, as we approach what feels like the summit of the story, let us step back and think about what rogue planets ultimately tell us about the nature of the universe. We live in a universe that is, by most measures, hostile to life. The vast majority of space is cold, dark, and empty. The conditions that support complex chemistry and biological evolution are rare and fragile, sustained by the specific combination of factors that produce a habitable world around a stable star. We have found one such world, and we have not yet found another. The discovery of life anywhere beyond Earth, which has not yet occurred, would be the most significant scientific discovery in human history. Rogue planets expand the conceptual universe of places where that discovery might eventually be made. They suggest that the galaxy is more complex and more varied in its planetary inventory than our star-centric view has shown. They force us to confront the possibility that the concept of habitable is more elastic than we assumed, that life's requirements are more flexible than we modeled, that the darkness between the stars is not quite as empty and inert as it appears. At the same time, rogue planets remind us of the impermanence of the conditions that make life possible. They are the discarded children of stellar systems, worlds that once had warmth and light and that lost it. Perhaps before any life could gain a foothold, perhaps after life had already begun. They carry the record of their past, in their geology, their chemistry, their internal heat, but they carry it in silence and darkness, with no living witnesses, with no biosphere to interpret and transmit the story. They are archives without readers. Libraries in the dark. There is a school of thought in philosophy of science, associated particularly with the late Carl Sagan, that says the universe is neither hostile nor friendly to us, it is indifferent. It operates according to physical laws that have no preference for the existence of life or consciousness or civilization. Life and consciousness exist, when they do, not because the universe favors them, but because the laws of physics permit their emergence under the right conditions. The rogue planet is a manifestation of this indifference. The same gravitational dynamics that build planetary systems also destroy them, that bring worlds into being also throw them out. There is no malice and no benevolence in the process. There is only physics. And yet, against this backdrop of physical indifference, the emergence of life, of organisms that can contemplate the universe, that can ask what is out there, that can build telescopes and write equations and send spacecraft to other worlds, is, by any reasonable measure, extraordinary. We are the universe becoming aware of itself, as Sagan and others have beautifully expressed it. And part of becoming aware of the universe is becoming aware of its rogue planets, its dark wanderers, its exiled worlds, its libraries in the dark. The fact that we have discovered these objects, that we have detected them through the momentary flicker of gravitational microlensing, that we have found them glowing faintly in the infrared of stellar nurseries, that we have begun to build the theoretical frameworks for understanding their origin and evolution and potential habitability. All of this is itself a remarkable testament to what the emergence of scientific curiosity and technological capability has made possible in the universe. We are, to use an image that has stuck with me since I first encountered it in the context of this topic, like people living on an island in a vast and dark ocean, looking out at the water and beginning to realize that there are other islands out there, dark, unseen, perhaps inhabited, perhaps not, and that the water between them is not empty but full of things we are only beginning to learn to see. Now let's bring the story forward in time, to the present moment and to the specific questions that are on the minds of the scientists who study rogue planets right now. One of the most actively discussed topics in the rogue planet community at the moment is the question of how to most effectively use the combination of the James Webb Space Telescope and the Nancy Grace Roman Space Telescope to constrain the mass function of free-floating planetary mass objects down to Earth mass scales. This is a fundamentally important question because the mass distribution of rogue planets, how many there are at each mass, from Jupiter mass all the way down to Mars mass and perhaps smaller, is the observational constraint that most directly tests models of planetary system formation. Current constraints from microlensing surveys suggest that there may be a large population of Earth mass free-floating planets, possibly more abundant than Jupiter mass rogue planets, consistent with the general expectation from planetary formation models that smaller planets should be more common than large ones. But these constraints are still very uncertain, because the events produced by Earth mass lenses are so brief, lasting only a few hours, that they are extremely difficult to detect reliably from the ground. Roman is specifically designed to address this, and the scientific community is eagerly anticipating the results of Roman's microlensing survey, expected to begin producing data in the latter half of the 2020s. There is also the ongoing and fascinating question of whether any rogue planets exist close enough to Earth to be directly detected and characterized. The closest known star to Earth is Proxima Centauri, at 4.2 light-years. Various analyses have placed rough limits on the presence of large, bright rogue planets within a few light-years, but these limits are loose. A cold, old, dark rogue planet of Earth size could easily be lurking within 1 or 2 light-years of Earth without our knowing it. Some researchers have proposed targeted searches for nearby rogue planets using either deep infrared imaging surveys or the distinctive signatures they would leave in near-future astrometric or parallax measurements. Finding a rogue planet within a few light-years of Earth would be a transformative event for the field. Not just because it would give us a close-up target for detailed study, but because it would confirm that the interstellar neighborhood is as densely populated with these dark worlds as the statistics suggest. It would make the abstract population statistics concrete and visceral in a way that galactic-scale surveys cannot. There is also exciting work happening on the theoretical side, exploring the long-term thermal evolution of rogue planets in unprecedented detail. Researchers including Dimitar Sasolov at the Harvard-Smithsonian Center for Astrophysics and various groups in Europe and Japan have been developing increasingly sophisticated models of how rogue planets evolve over billions of years. How their heat dissipates, how their atmospheres evolve, how their interior structures change, and under what conditions they might maintain liquid water for geologically significant periods. These models are being refined and compared against the growing observational data from infrared surveys of young free-floating objects, creating a productive interplay between theory and observation. The question of whether rogue planets could host prebiotic chemistry, the chemical reactions that might precede and potentially lead to the origin of life, is also being explored with increasing rigor. Laboratory experiments simulating the conditions of rogue planet interiors, high pressure, moderate temperature, liquid water, mineral interfaces, no sunlight, are being conducted to see whether the kinds of chemical reactions associated with the origin of life on Earth can proceed under those conditions. The results so far are cautiously encouraging in some respects, though the field is young and the extrapolation from laboratory chemistry to planetary biology is always fraught with uncertainties. One of the most important open questions is the longevity of liquid water in rogue planet interiors. For a rocky planet with Earth-like composition and mass, radiogenic heating declines over time as the radioactive isotopes decay. The half-lives of the relevant isotopes, uranium-238 is about 4.5 billion years, uranium-235 is about 0.7 billion years, thorium-232 is about 14 billion years, potassium-40 is about 1.2 billion years. Mean that radiogenic heating was significantly stronger in the early solar system than it is now, and will continue to decline as those isotopes are exhausted. Over timescales of tens of billions of years, even a large rocky rogue planet will eventually cool to the point where any subsurface ocean freezes completely. The timescales for this cooling are uncertain and depend on the specific composition of the planet, its size, and the thickness of any insulating ice layer. For the most favorable combinations of parameters, a large rocky planet with a high initial radioactive content, covered by a thick insulating ice layer, the lifetime of liquid water might extend to tens of billions of years. For less favorable configurations, it might be only a few billion years. Given that complex life on Earth took roughly 3 to 4 billion years to evolve from the earliest known life, a rogue planet with only a few billion years of liquid water might not have enough time to evolve complex life even if simpler chemistry gets started. But a rogue planet that maintains liquid water for tens of billions of years might have far more time than Earth has had. The universe is under no obligation to match Earth's timeline for the evolution of complexity. As we draw toward the close of this exploration, though it is a story with no real end, because the science is ongoing and the universe continues to reveal its mysteries on its own schedule, let's consider what the study of rogue planets reveals about the nature of scientific exploration itself. Science is often told as a story of light, of the illumination of ignorance, the revelation of truth, the brightening of understanding. And there is truth in that framing. But the story of rogue planets is a story about learning to see in the dark. It is about developing tools and techniques specifically designed to detect what produces no light, to infer the existence of something from its gravitational shadow, its thermal whisper, the briefest moment of borrowed brightness as it drifts past a distant star. It is about being willing to look in places that our intuition tells us are empty and finding that they are full of things we could not previously have imagined. The rogue planet story is a story about the limits of our default assumptions and what happens when we dare to challenge them. For decades, the implicit assumption in exoplanet science was that planets need stars, that the study of planets and the study of stars are inextricably linked, because that is how we detect planets, and that is how we think about planetary habitability. The discovery of the rogue planet population, still in its infancy, still rough and uncertain in its details, challenges that assumption at the most fundamental level. Planets don't need stars. Stars don't make all the planet mass objects. The galaxy has more kinds of worlds than we built our models to accommodate, and the models must now grow to account for them. This kind of paradigm expansion, not quite a paradigm shift in the Kuhnian sense, but a significant broadening of the conceptual space of what is possible, is one of the most exciting things that can happen in a scientific field. It doesn't invalidate what was learned before. The planet formation models that have been built over decades of careful observation and theory are not wrong. They are incomplete in ways that the rogue planet population is helping to reveal. That incompleteness is not a failure. It is an invitation to do better science. And the implications extend beyond planetary science. If there are hundreds of billions of rogue planets in the Milky Way, if even a fraction of them have conditions suitable for liquid water and prebiotic chemistry, then the question of life in the universe cannot be answered by looking only at the habitable zones of sun-like stars. It requires a broader, bolder, more imaginative conception of what habitable means and where habitable conditions might be found. It requires the willingness to search for life not just in the light, but in the dark. Let's take one final sweeping look at what we know and what we still don't know. A kind of grand inventory of the rogue planet story as it stands today. We know that rogue planets exist. Multiple lines of evidence, gravitational microlensing surveys, direct infrared detection of free-floating planetary mass objects in stellar nurseries, statistical analyses of moving group members, all confirm the existence of planet mass objects that are not gravitationally bound to any star. We know that they are common. The microlensing surveys, taken at face value, suggest that rogue planets are at least as numerous as stars in the Milky Way, and possibly significantly more numerous. The precise ratio depends on the mass scale and is still uncertain, but the broad conclusion that rogue planets are a major component of the galaxy's planetary population appears robust. We know that they form by at least two distinct mechanisms: ejection from stellar systems and direct formation by gravitational collapse, and that distinguishing between these mechanisms for any individual object is difficult but important for understanding planetary and stellar formation. We know that young rogue planets are warm and detectable in infrared, giving us a window into their properties and compositions that older, colder rogue planets do not provide. We know that, in principle, the interiors of rogue planets could remain warm enough for liquid water for billions of years, sustained by radiogenic heating from the decay of radioactive elements. We know that life on Earth exists in environments with no sunlight, sustained by geothermal energy, and that this demonstrates the in-principle possibility of life in similar environments on rogue planets, though such life has not been detected. We know that future observatories, Roman, Rubin, and potentially future infrared missions, will dramatically improve our ability to detect and characterize rogue planets, particularly in the Earth mass range. We do not yet know the precise mass function of the rogue planet population. How many rogue planets there are at each mass scale. We do not yet know what fraction of rogue planets were ejected from stellar systems versus formed in isolation, and whether this fraction depends on the properties of the galaxy or the star-forming environment. We do not yet know whether any rogue planet harbors life, or whether the conditions for life's origin or persistence are met in any rogue planet's interior. We do not yet know whether any rogue planet has ever passed close enough to the solar system to leave detectable traces, or whether any material in the solar system originated from a rogue planet. We do not yet know whether the strange binary planetary mass objects discovered by the James Webb Space Telescope in the Orion Nebula, the jumbos, represent a new category of astrophysical object that requires new theoretical frameworks to explain. And we do not yet know, in the fullest sense, what the rogue planet population means for the probability of life in the universe. Whether these dark, wandering worlds are mostly sterile monuments to failed habitability, or whether some of them carry, in their dark and frozen interiors, the tenacious, improbable, extraordinary thing that we call life. These unknowns are not sources of frustration. They are the leading edge of one of the most exciting scientific stories of our time. They are the places where new knowledge will be made, where careers will be built, where discoveries will be announced that will change the way we think about our place in the universe. The story of rogue planets is ultimately a story about vastness and variety, about a universe that is more complex and more full of worlds than we had any reason to expect, and about the human capacity to detect, contemplate, and begin to understand even the darkest and most remote of those worlds. It is a story that started with a theoretical prediction, evolved through decades of patient observation, was illuminated by flashes of gravitational light borrowed from distant stars, and now stands at the threshold of a new era of discovery powered by the most capable telescopes ever built. And when those telescopes deliver their full harvest of data, when the Roman Space Telescope has cataloged thousands of rogue planet signatures in the galactic bulge, when the James Webb Space Telescope has surveyed stellar nursery after stellar nursery revealing the population of free-floating planetary mass objects in each, when we have enough data to begin answering the question of how many of these worlds might have the conditions for life, we will look back at this moment as the beginning of something. The beginning of the rogue planet era of astronomy. The beginning of a real, data-driven reckoning with the full inventory of worlds in the galaxy. The beginning of a conversation about what it means for the universe's potential for life if even the darkest and most isolated corners of the interstellar medium are populated with worlds that carry, deep within their frozen shells, the warmth needed to sustain chemistry. There are hundreds of billions of rogue planets in the Milky Way alone. Hundreds of billions. Each one a world. Each one with its own history of formation and, for the ejected ones, its own story of loss. Each one traveling in silence and darkness through the long years of cosmic time. And somewhere among those hundreds of billions of worlds, somewhere in that vast dark inventory of wandering planets, there may be something small and chemical and stubborn, clinging to the warmth of an ancient radioactive decay, doing what life does everywhere it can, persisting, replicating, evolving, and waiting to be found. The universe's wanderers are everywhere, and we are only just beginning to see them. Now, think about this for a moment, and sit with it as long as you need to. The night sky that you look at, filled with the light of hundreds of billions of stars, is hiding something. Between every pair of stars you can see, in the absolute darkness that your eye perceives as empty space, there are almost certainly rogue planets drifting silently past. At this very moment, somewhere between us and a star in any direction you look, a dark and frozen world is crossing the line of sight, bending space ever so slightly, leaving its ghostly gravitational fingerprint in the light of a star we will never visit. We cannot see it. We cannot feel its passage. We have no way of knowing it is there, in that specific moment, in that specific place. But it is there. It was always there, even before we knew to look for it. Even before we had the word for it, or the mathematics to describe its motion, or the telescopes to detect its shadow. These wanderers have been moving through the galaxy for billions of years, completely indifferent to whether any creature on any world has ever paused to notice them or wonder about them. That we have paused to notice them. That we have looked at a momentary brightening in a distant star's light and said, something is passing there, something dark and heavy and world-sized, is itself one of the most remarkable achievements of the species that evolved on a warm, blue, light-drenched world orbiting an ordinary star in the outer reaches of a spiral galaxy that is itself just one of hundreds of billions of galaxies in the observable universe. We found the darkness. We measured it. We gave it a name. And we are beginning, just beginning, to understand what it might contain. That, perhaps, is the deepest thing the rogue planets have to teach us. Not just about the nature of the cosmos, but about what it means to be the kind of creature who cannot resist asking what is out there in the dark, and who will not rest until they find out. The wanderers wait, and we are watching.